All right, now let's try this sample problem. What we have right here is we've got a mule and two farmhands are trying to pull this mule into the pen. And so the force one, this one right here, exerted by the first farmhand, is represented by this vector, 1 Newton I hat plus 5 newtons J hat. This farmhand is pulling with this force, 3 newtons I hat plus 2 newtons J hat. And again, this doesn't add up to 5. These are vectors, so we have to add them vectorially. But I've already done that. Here are the vectors represented, one here and one here. Those two arrows right here and here. This, however, is the overall displacement of the mule. The mule is fighting and trying to resist this. So the displacement of the mule is this. Doesn't go in the direction of either of these farmhands that they're pulling. So in order to figure out the work done by the farmhands on the mule, and hence figure out how much the change in kinetic energy of the mule is, we got to do a dot product. F net dotted on R, the displacement. Well, the great thing is if you have unit vectors all set, dot products become incredibly simple. In fact, we won't have to figure out a single angle here. What we're going to do is first find the net force. So all we got to do is look at our unit vector notation. Force 1 has a horizontal force of 1 Newton. Force 2 has a horizontal force of 3 newtons. So the net force in the horizontal direction is 4 newtons I hat. 4 newtons in the horizontal direction. Then in the y direction, we notice that force 1 has a force of 5 newtons J hat, and force 2 has a vertical component of 2 newtons J hat. Add those together, 5 and 2 gives us 7 newtons J hat. So we have our net force all set for us to dot onto our displacement. It's as simple as foil. So first, 4 newtons I hat dotted on 4 meters I hat. Oh, that's 16 joules. That's easy right there. Outside 4 newtons I hat dotted on 5 meters J hat, those are perpendicular to each other. So this dotted on this gives us nothing. Don't even have to include that. Inside, that'll be 7 newtons J hat dotted on 4 meters I hat. Again, perpendicular, nothing. And finally, last is 7 newtons J hat dotted on 5 meters J hat. Now those are parallel, so there is a non-zero dot product. It's 35 joules. So here's what we get. Notice for the dot product, we just got to add these up. It's a scalar. We don't have to worry about any direction. And we get the net work done on the mule is 51 joules. And that's all there is to it. You know what? There's no direction to work or energy for that matter. It's just an amount. 51 joules of work has been done. What's the change in kinetic energy of the mule going to be? Assuming that the mule does no work, the change in kinetic energy will be the same thing. 51 joules. That will be it. Let's do another example right here. Work done by a spring. Now the trick on this one is that we do have a changing force. And hopefully from last year you are acquainted with Hooke's law. Hooke's law is simply this, that the force exerted by a spring is in the opposite direction of the displacement, and it's equal to, it's proportional to the displacement of the spring, how much you stretch it or compress it, by this proportionality factor, which we call the spring constant K. And you'll notice that this negative sign right there is there because the force that the spring exerts is always opposite to the way that you pull or push the spring. So let's take a look at the situation, what we got. What I'm looking at is a situation in which we have an object which is, here's our spring at equilibrium. So there's the spring just at rest. There's no forces on it. That's just its natural length. So what we do is we attach a block to it and we pull it back to negative x. And then we let this thing go and it springs back. It ends up going to this, back to the equilibrium point. So if I have a changing force, I got to figure out the area under a curve. It's not a constant force. I can't just do F dot delta x because the force is changing. There's no one force. Now, yes, you could use the average force. That's true. But you got to be careful with that because sometimes the average force will be 0 for the entire motion. Here, we're just going to look for the motion until it gets back to equilibrium. So let's figure out what the work done by the spring is. And notice that we don't want the work done on the spring. We want to figure out the work done by the spring. So here's how we do this. Well, we start this off right up here. This value right here is kx. How do I know that? Because if the spring has been pulled a displacement negative x, it's going to be pulling forward with a force kx according to Hooke's law. So the force starts out as kx when it's right over here. But as it compresses back to its equilibrium, I shouldn't say compress, it just unstretches back to its equilibrium point, the force goes down. The force is a function negative kx. So it goes down to there, and by the time it's back to the equilibrium point, the force is back to 0 right here. So it starts off at kx, and it ends up at 0. To figure out the work done by the spring, we just calculate this area under the curve. How do I do that? Well, I know this distance right here is x. This distance up here is kx. What's the area under a triangle? The area of a triangle, very simply, 1/2 base times height, and that's this. So the work done by a spring is plus or minus 1/2 kx squared. I put the plus or minus in there because you got to determine, is the force in the same direction as the displacement, or is the force in the opposite direction of the displacement? For our example here, the force is in the same direction. Notice that it's going to be positive work done by the spring, even though I'm starting at negative x. That doesn't matter. The displacement is this way to the right, and so is the force. So it's going to be positive 1/2 kx squared. Now, if it gets back to there, this is not the same x. This is x2, I'll call that. Let's try to figure out how much work is done by the spring if it only gets back to right there, x2. Again, we're going to find the area under the curve. So what I got to do is I got to add up this area right here. That's how much work the spring did on the way to the equilibrium point. But then I've got to also add up this work done right here. And importantly, notice that this work is negative. Why is that? Well, think about which way is the spring pushing when the object is over here. Let's take a look at that. Which way is, when it's over here, which way is this spring exerting a force? It's resisting, it's pushing the object to the left, but it's still moving to the right. The velocity is still to the right. So the spring is doing, for this part of the motion, negative work. The force is to the left, the displacement's to the right. The angle between them is 180 degrees. That's going to give us a -1 for our cosine theta. So notice that we got to add these two values up here. We got work of the spring is 1/2 kx1 squared. That was this work that we did up here. But then we're going to take away this second little triangle because that is negative work. That's the total work. And again, notice the area under the curve is always a change. In this case, what is the change? It is a change in K, change in kinetic energy. You may use KE for K. Most of the textbook will use just K for kinetic energy, but you're welcome to use KE. That's completely legitimate. So areas under the curves always change. In this case, the area under the force versus displacement curve is the change in kinetic energy. The total work done, change in kinetic energy.